Good morning. Let's resume our discussion. So what are we discussing in the previous class? Can one of you brief, or can couple of you brief? What is that we were discussing in the last classes?
We were discussing about HOG as a feature and how it's very powerful in classifying whether it's a human or not. And then we started with image features in classification, for which we saw how to form image mosaic using various transformations, displacement models. And then we concluded with an idea of face detections and features, which could be simplified using simple rectangular features.
Very good. So let's resume our discussion. We will discuss in this class more on the face recognition, face detection task with the same set of features that we were discussing before. And then we will discuss a little bit more on the feature extraction, especially how do we extract features at multiple scales, or how do we extract robust features, or how do we find the feature points also across scales or in a more robust way. In the sense, robust means they are stable across different scales, resolutions, and so on. And they're independent, invariant to geometric and photometric variations. So we'll see those things. So let's resume our discussion with face detection. As we mentioned in the last class, this is the very celebrated application of computer vision. How to extract a very simple set of features, how to very effectively come up with an algorithm that will enable us to extract the features much faster, and subsequently develop an algorithm or a classification framework or a learning-based framework, which will enable these features to learn the objective of classifying a face or not here in a given patch, and then finally detect the faces. So as I mentioned before, after the initial like one of previous developments, that Harris corner detector for feature detection or key point detection, and the histogram of orientation gradients for feature extraction, in parallel lines are around the same years. This is also a celebrated application of computer vision. So the objective here is to detect the faces in real time, so that the objective posed by them, Viola-Jones robust real-time object detection, they constrain themselves to face detection. So the method consists of four major steps. First is identifying good features. Which are good features? Good means simple and computationally very easy to compute and very effective. And we may have a large number of features at the beginning. That's okay for them. So they started with having a large number of simple features. And the second step of the algorithm that is proposed by Viola-Jones for face detection includes how to effectively find this. See, as we mentioned, we want to perform a real-time face detection. The detection has to be as fast as possible. And the features that we would like to extract are also many. So how do we do it very effectively? Through any other intermediate means. So that's integral image concept. And this integral image concept has been used in computer vision quite a lot of other applications as well. So that's that indicates how effectively, if we have a solution or a idea on something to be done, how effectively to do it. In sense, it's a means or mechanism to perform the identified task. And then the third step in this face detection algorithm is a classifier, as I mentioned, Adaboost algorithm. So this is an effective classification method that will help us to select from many features that I mentioned at the beginning to a small set of features. And that does through learning. And finally, there is a cascading stage. This is also one of the key suggestions or the key concepts in computer vision to deal a problem. So this example of face detection not only gives an understanding of how feature extraction can be done, but this also gives us an idea on, along with the feature extraction, how do we do a given task effectively through learning, and also how do we do it through some other simple tricks guided by the application. And as this is not very specific to application, and this is generic in few other applications or many other applications as well. So the basic idea, as we discussed in the last class, is to identify features, very simple or simplest features that will help us to identify face. That is, the eyes region is relatively darker than the other regions in the face. That's the simple idea. And for that, what they have resorted to extract such features are only binary plus or minus operations without any multiplication. See, if we would like to extract features with any convolution or with any non-binary mask or non-binary kernel with convolution, we need so many number of operations. But if we would like to perform with only binary like plus one, like 1 0 or 1 minus 1 kind of mask, then simply additions, algebraic operations are only required. No multiplications are required. So the other important aspect in computer vision methods evolution is not just to develop a method or in software, but also have them in embedded platforms. So if we would like to have it a real-time operation for this, so it has to be fit in an embedded platform or equipment as well. So for example, in all our smart cameras, we see that face detection happening. So it's not done through a other external device for processing. So the processing has to be as simple as possible, and it should be the embedded through a little bit of hardware or even software within the equipment. So it has to be as light as possible. Light meaning the number of operations to perform a task are much smaller. So they made their feature extraction only with additions and subtraction, algebraic operations. And this algebraic operation is through different kind of masks or different kind of filters that we will see. Different sizes of filters and different shapes of filters, but all having only +1 -1. So the essential steps in the overall approach, as I mentioned, it has first feature extraction. This is called Haar features. The reason being, those who are a little bit aware of the other signal processing aspects like wavelet transform. Haar wavelet is a well-known wavelet which also is useful for extracting different frequency information in the signal through plus and minus operations. Essentially, Haar wavelet also does a plus minus operations, except that there is a normalizing term 1/√2 or something like that. So the Haar wavelet is what is the resemblance of this feature extraction. So that they named it as Haar features. This is the name they have given first in computer vision, based on the wavelet features that are already there since long. And the procedure to perform it, as I mentioned, is the integral image. And subsequently, they applied an algorithm that's an ensemble classifier, which I will discuss later, for classification. And the procedure they followed to decide a face or not is through a cascading approach. This cascading approach is also very well known in computer vision. Say, for example, if you would like to identify a face in 1000 x 1000 images, faces or face in 1000 x 1000 images, the easy task is to throw out the all non-face regions, and then only where we have a doubt of having a face or some information, there only we will process further and say that this is the face. So that kind of approach is well known, and it is proposed in face detection first by these people. So if in a given image, what we do now is see the regions where there is no information at all and throw them out and saying that there is no face. And then we can confine ourselves from 1000 x 1000 images where we may have 10⁶ patches, or at least 10⁵ patches. We may confine now to only less than 50% of the patches. Because you can throw away many regions just saying that there is no information at all at those regions. Can one of you tell what are those such regions where there may be no information in the image or not much information in the image?
Like in cases of face, the background can be
Background.
Yeah, background. More descriptively conveying the uniform regions. Okay, wherever the if a given patch is uniform, in that region you will not have any information as such. Face will not be there, or the object of interest may not be there or will not be there. So throw away the regions, uniform regions. What do you think is a good procedure, mathematical procedure to throw away such regions? Any idea? Say I want to throw away all uniform regions. I keep taking the patches in a 1000x1000 image. Say 30x30 patches. Okay, I start and keep taking. Okay, and each patch I will see if a patch doesn't have a information that is uniform, then I will throw away. So do you think any mathematical measure will help me to perform this task? What should I compute in that patch to see whether it is a uniform region or non-uniform region?
Simple gradient.
Gradient, fine, but I want to quantify with a single number. I don't want to have the gradient information at all pixels 30x30. Any other, even gradient, with the help of gradient, how do we quantify with a single number? That's the question. Yeah, this is very important procedure in computer vision. Usually the procedure in computer vision lies understanding the physical problem, okay, and then identifying intuitively or through the existing literature and the developments, some approach for dealing with it intuitively, in the sense that it's a conceptual algorithm, bringing that to the mathematics. That is the next step. After you bring it to the mathematics, how do you optimize and get a solution? That is the last step. These are the essential steps in dealing with almost all computer vision tasks. Now, given this, okay, we are at the stage 2 now, where we have the idea that we want to throw out a uniform regions, and we need a very single quantitative clue for throwing out the uniform regions. Okay, what do you think is that clue? Gradient, fine, but how does it help as a single quantitative measure for throwing out a patch, saying that it is uniform? Yeah, can you take it forward, Abhimanyu?
If the gradient is 0 or constant, we can quantify it as a uniform.
No, the question is, you should have a single quantitative measure. Gradient is operation gives gradient at all pixels, right?
Yes, sir.
Yeah. So how do you get a single quantitative measure from that?
Histogram orientation.
Okay, histogram orientation, gradients is also a histogram. It's a vector. Is it not? Histogram means 10 bins you take, 20 bins you take. For each bin, you count the gradient angles. I just need a single number to say that it's a uniform region, throw away. It's a very crude, fine. But I want to start with a crude measure and throw out a very confident cases. Only if it is strictly uniform, I will throw out. Otherwise, I will keep and examine further for face. Okay. Further, any further idea on how do we use the gradients information? Assume that we have the gradient information only. How do I use it as a single quantitative measure for that patch? The answer should be very simple.
Like we can multiply someone with ones and someone with minus ones.
Okay,
Like
the question is, if you multiply someone with ones and someone with minus ones, what will we get? Again, an image, right? You have a 30x30 gradient information there.
But if we sum that,
right, that's the answer. That's all. Why you want to multiply +1 and -1 again?
to get to make 0, like some number, like if there is any change, we get some number, otherwise 0, right?
No, but why do you need it? See, your answer should be in this way. If I have a patch, I just want to say whether that patch is uniform or non-uniform. Okay, I have the gradient information also is given. What is the single quantitative measure that will help me?
Sum of gradients.
Sum of gradients. That's all. Sum of gradients, if it is greater than a threshold, okay, I say that there is some information there. If it is zero strictly, no information there. Fine. Sum of absolute gradients will give me even better information because gradient can be positive and negative. Is it not? Sum of absolute gradients gives me. But even there is a better measure to quantify uniformity in a patch. What is that measure? If I give you a patch, okay, to quantify the uniformity in a patch, there is a better measure. What do you think is that? You're all have done several mathematics courses. What is the quantitative measure that quantifies the uniformity in a patch or in a signal? Non-uniformity in a signal. So what is that to quantify non-uniformity in a signal? I'm just trying to see a big image. Okay. So can one of you throw the word that will quantify the non-uniformity in a big, given patch or a given signal, even one-dimensional signal? I will give you a set of numbers. Okay, 1 to 100. I just want to know how similar they are or how dissimilar they are, how non-uniform they are. What will you do? 1 to 100, just I have given some numbers. 1, 1, 1, 100 times I have given, okay, as one chunk of numbers. And then 1, 2, 3, 4 up to 100 I have given. Okay, I want to know how non-uniform they are or how uniform they are, these two. Like these two set of numbers, which are uniform, which are not uniform. What is the measure you people use?
Correlation.
Okay, will you use correlation? I don't want to see similarity between these two sets. Have a set of numbers 1, 1, 1, 1, all ones, 100 ones. Okay, other side 1, 2, 3, 4 up to 100.
Variance.
Well, yeah, can you tell louder?
Variance.
That's all is the measure, right? So variance is the measure which will give the uniformity of a patch or a signal. So you the people that has to strike at the first instant itself, right? So that's how the methods have been developed in computer vision. So they wanted to throw away all non-uniform regions. Okay, and then the measure of uniformity is the variance. Okay, inverse measure of uniformity is variance. You just see the variance. If variance is close to 0, throw away. That's all. That's not a patch, possibly with phase. That doesn't have any information. Just straight away throw away. So by that, in a given image, if it is 1000 cross 1000 image, you can throw away almost say even 30%, 70% of the regions. Only you have now 30% of the regions where you need to take a call. Is there an information? If that information is already there now, given that it is not thrown away, is it a phase or not? That is stage 2. Okay, and then there we will try to see some feature extraction and so on in those regions only. Why to do feature extraction for all regions? And then decide based on the features and the learning of the classifier, is it a phase or not? Okay, that's the approach these people have followed. And I will skip some of these things as we discussed already. So the eye region is much darker than the others. That's the main idea. And then the other thing to see is the size keep varying. So we have to see the features at different scales or different resolutions. So as I mentioned, the features that they have selected to identify a phase region are Haar features. So as you can see here, Haar features, as I mentioned, they are +1 -1 is essentially a wavelet which gives a frequency information in a signal. That means if signal is rapidly varying, if I just convolve with +1 -1 +1 -1 etc., its value at each location will be high. If a signal is uniform, if I convolve with +1 -1 +1 -1, then what will happen? Its value at each location will be 0. Okay, so this gives a fair idea of is it a uniform signal or a high frequency signal. If it is varying in between, okay, somewhere it is varying, somewhere it is smoothly varying, etc. Somewhere, so in some locations it will have high value. If I convolve with 1 -1, in some other regions it is 0. Okay, so it's a intermediate frequency we can consider. So like that, the wavelets are designed to identify different frequencies, usually in the signals. Here, the same concept can also be used to identify where the variation in the phase is very high. Okay, you can see that around the eyes region, the variation is very high. Okay, so and to capture that, what they have made is they have made different kind of filters with different orientation, but all with algebraic sum of plus minus one kind of filters, simple to compute filters. So they have actually filter 1 here, filter 2, filter 3, filter 4 types of filters. Okay, each of these are at different scales, taken at different scales, because each time the phase will not appear in the same scale. You may have at different scales, at different images or at different distances from the cameras when we capture the face. They have, in fact, I think 5 types. So they convolve with all 5 types and get the features, not just in one scale, but at several scales. So all these filters, if you see, what they require is sum in one region, okay, and then sum in another region, sum of pixels in this region, okay, sum of pixels in this region you perform, and then subtract the sum of pixels in this region within sum of pixels in this region. Similarly, if I want to apply this filter, what essentially I need to do on an image is extract the sum of pixels in this region, sum of pixels in this region. If this is -1 and this is 1, 1 minus 1, some here minus some here. That's the filter value or the filtered value at this location. Similarly, all these filters, what they require is summation in different regions. This may be 3x3 region, this may be 5x5 region, or this may be even 20x20 region, okay, or 15x15 region. If the whole image is 30x30, this may be even 15x15 also. They perform like that because the whole image 30x30 patch can be a single phase or only part of phase. So like that. So these each of these blocks represent a set of pixels. We sum all the positive pixels and then negative pixels are all the pixels in one white box, all the pixels in the black box, and subtract the white box pixels with the black box pixels. And that's how the filtering happens at each location. So essentially what is important or key and common in all these things is summing of the pixels in a given block. So how do we get the sum of pixels in a given block? Because the block size keep varying when I apply different resolution filters. One time the filter may be of this size, one time filter may be of this size, and sometime filter may be of this size. Okay, so each size I need to sum across different patches. So what they have made is they initially made an intermediate space called integral image. The integral image, what it does is it just sums the elements in a patch. Okay, from starting from here. Okay, the sum is here. It sums along this. So it happens in a zigzag manner, I think. So here sum is up to here. Okay, and here sum is up to here, if I am correct. Okay, here sum is up to here, and here sum is up to here, like that. So it keeps going, sum here, and then sum is here, but up to here. Okay, and then up to here, and so on. So up to say from here, the sum will be up to here. So that some integral image will give me a like this is the expression for all x less than or equal to x, y less than or equal to y. They perform integral image and put it, and such integral image that they keep summing it with the previous location and give the value. So essentially, as you can understand, this is a kind of intermediate representation, which will, this is the sum of all elements. Okay, and then this is the sum of elements up to here, like that. So once we get this intermediate representation, they have made a small step to compute any patch, the sum of elements in any patch. Sum of elements in any patch is obtained, say D patch if you would like to do. So then what we do, first make the whole sum, then make this sum anyway you have at this location. Up to here you have the sum in this location B. Up to here you have the sum in this location 3. Then D is equal to what? D is equal to the total sum which we have at this location 4 minus 2 minus 3 plus 1. Because we are summing this, we are subtracting this 2 times. Okay, we will add this 2D to get the only D block. 4 plus 1 minus 2 minus 3. That essentially gives us the D. Like that, any patch, sum on any patch can be computed. Once we have sum on any patch, applying filter is nothing but you just see the filter at that location. Is it a white or black or a positive or negative? And then appropriately put the sign and make the, say, if I want to perform B minus D, take the first sum of elements in B, sum of elements in D, and then simply D minus B I will perform. Okay. Similarly, any other operation, any other filters can be done. So I am skipping the details. Hope you can compute with the small examples and confirm what I am conveying. So this is exactly how they perform. They first will have the integral image. Here the color indicates the higher values. Red is high value and then blue is 0 value. And you can see that if I want to perform a sum here or feature extraction here, what I do is I will put a filter here. Sum of the all elements in this block I will get. How do I get? This value at this location in integral image plus this value minus this value minus this value. Similarly, sum in this patch I need this minus this plus this. Okay, and I have some here, I have some here. This minus this will give me the value here. Okay, for the convolution with this scanner. Like that, we can perform any number of feature extractions. Okay, and then what they have done is since the size of the face is not known, so we perform the feature extraction at different scales. So starting from a small scale, which is shown here, to a much bigger scale. So you can see that this is a small scale, this is bigger scale. They will perform the whole, even bigger scale and so on. So this is again, this is one scale and we perform at different scale with different 5 different kind of filters. And that has to be done at each location because the face can be small, face can be here. So this just doing with different scales is not sufficient. Doing with different shifts is also necessary. So we may perform a shift here and perform the feature extraction here. Okay, so because the face is in small region here, I should the nose, eyes region is here, I should be able to locate. So similarly here, all those, the face can be in any location. So for all shifts, for all scales, we extract the features with all filters. Okay, once we do that, for different aspect ratios as well. Sometimes this is the face may be wider or the eyes and nose regions may be wider. Sometimes it may not be wider, narrower. So if we perform all such operations on 24 cross 24 image, the number of features we get is 1.6 lakhs plus features. So as you can see, there are a lot number of features that we will get because we are doing with different shifts, different scales and different filters. Now the question is, feature extraction is done very effectively, and this is done through a concept of integral image as an intermediate step, and very simple features they devised. But now the problem or the question is, how do I identify from this large set of features which are a very prominent features that help me to identify the face region? Initially itself, they can't take that, okay, you take only this kind of features and this kind of features, throw away all others. Because sometimes we may have a slightly cross information. So eyes here and nose here, that also gives some information. So they want to identify all potential features in this, say, 160,000 features. So they roughly want to identify 200 features are so which are prominent in this. So now if you would like to do that, we should have a select feature selection algorithm or effective algorithm which will select the very good features. So that is done through an algorithm called Adaboost Classifier. So this is a ensemble classifier. So I will not go into the too much details into this. The aim is not to convey you what Adaboost algorithm does or full theory of Adaboost algorithm. It has its own theory, how it has evolved. But to give an idea how the classifiers have been designed in computer vision before advent of this deep learning and so on. So what the Adaboost algorithm does is, it assumes each feature, okay, when we compute, it gives us a clue of face or not face. That means each feature is a simple classifier, enables us for a simple classifier. That means if I just see at a given location and say that, so here, say this location, if I put a feature block and say that there is no, say if I perform this operation, it has to be greater than threshold for having a face, assume that. And now if I put this at this location, the value is not greater than threshold. So I just simply throw away with this feature at this location that it is not a face. Okay. So that's the simple classifier, array based classifier. If I put this at this location, I may be able to say that the threshold is greater than some value, or the correlation with this filter is greater than threshold. And then I say that it is a face. So the here classifier, so if I have 160,000 features, I have now 160,000 classifiers with me. Each feature telling the given patch at that location, is it a face or not? The overall 24 by 24, I want to decide whether there is a face or not in that. Okay, that's my objective. But what each feature is telling? Each feature is telling is that a whole patch, even if we consider 24 plus 24, is that patch having a face or not? It is telling. Okay, each feature is telling by its own vote. So we assume that if initially, if we assume all are equally likely voting, okay, say out of the 160,000 features, so some of them might have told that no face, face not being there. Some of them might be telling that face being there. So each is referred to as weak classifier. Okay. So it is +1 if it is greater than threshold, and -1 if it is less than threshold. +1 being a face is there, -1 being face is not there. Okay. Weak classifier, when it's trying to classify all the positive samples, these are all the faces, assume that all blue are the faces, all red are the non-faces. So if I just take a call on a single weak classifier saying that all these are faces, all these are non-faces, what's happening is in this region, I'm classifying so these are all faces, they're all non-faces. That is what is the weak classifier decision. So in that case, what is happening? We are misclassifying the non-face, non-face as face, okay, by this weak classifier, and face as non-face by this weak classifier. So what we do for those samples, we increase the weight. These samples will give us a like the inverse weight to impede that this classification is not correct or it is to be adjusted. And this classification boundary is adjusted such that we get a better classifier. Okay, so this classifier may be with the second another feature, but when we keep doing this, what we do is we get some set of good classifiers whose combination will give us a final correct classification. That means this is one weak classifier, initial weak classifier, saying that these are all non-faces, these are all faces. This is another classifier, this is another weak classifier saying that these are all faces, these are all non-faces. This is third weak classifier saying that these are all non-faces, this is the face. So now if we make an algebraic combination of these two, then what we may get is all the faces can be obtained. So that's the idea. The idea is each classifier, each weak classifier will take a only suboptimal decision or not a correct decision. But these second classifier will act in such a way that whichever the first classifier has misclassified, more importance to them is given for those patches to classify better. Okay, the third classifier will act in such a way that which are being misclassified by the first two classifiers, weak classifiers, will be better classified. Like that, these classifiers will perform classification, and then finally the combination of this will give us a better classifier. As you can see here, in each of these things, what we are doing is this is the first classifier, and this is the associated error, and then this is how we increase the size of the some of the samples where the patches have which patches ought to be concentrated more. So then we have the second classifier and then the third classifier, and combination of all these three classifiers will give us the final classifier. And this will correctly classify all positive samples as positive, faces as faces, non-faces as non-faces. Just to see the algorithm again, initially we start with equal weightage to all image patches. here weights are not to the classifiers, as I mentioned before. It is to the each image patch. So that means assume that we initially each image is correct, like all positive samples and the negative samples will get the equal weight at the beginning by the classifier, or when we perform classification while computing the error measure. Okay, so the error measure is for the classifier, but the weightage is on the image patches. So initially all are equally likely. So that means if we have M positive and L negative, 1/2M and 1/2L will be the weightage given to the positive patches and negative patches. Okay, and then what we do is we start with computing the error with a given first classifier. After we compute the error, we can see that the weightage to each image can be increased in such a way that the if it is correctly already classified by the first classifier, we no need to do anything more. But if it is not being correctly classified by the first classifier, we increase its weight such that it is more focused in the subsequent by the subsequent classifier. Like that, this weight is formulated, and like that we perform with each of the classifiers. Some of the classifiers are seen to show that good improvement in performing this classification or reducing this error better. Only those classifiers we consider as the classifiers of importance, and then we make a linear combination of such classifiers which increase the or which reduce the error or which increase the accuracy to formulate the final final strong classifier. Okay, this is referred to as Adaboost classification algorithm. So as you can see, it keep performing iteratively with classifier, the first classifier giving the weightage further to the samples, and then higher second classifier taking more importance or more focus on them, and so on. This is how the face. This is how the Adaboost learning is done in this framework. And with this, what they can do, they were able to do is they reduce the number of features to 200, and even that they have done in a like this is also done in a cascaded manner. So initially they start with some 20 features, and then based on 20 features, they have the ranking of these features based on the previous each week classifier, how much error does it gives. So based on that, what they do is they order the which is a good weak classifier. So if all 160,000 weak classifiers are considered at the beginning on the whole image samples, then if you order the errors, we can see that top 20 weak classifiers are this reasonably good weak classifiers, or with which we can start. So let us, what the algorithm does is take those 20 weak classifiers and make a combination as a strong classifier to reset some of them, and then add 20 more features. Okay, or test with other 20 more features, and then test other 20 more features. Testing with other 24 more features means testing with other 20 more classifiers. Like that they keep performing, and one passes all stages will be a phase. If any of the patch is thrown away at intermediate stage in Cascade, it is not a phase. That's how it was performed, and it's a at that time it's a very good success in terms of performing face detection in real time and 50 frames per second and with high accuracies. So most of the cameras has this Viola-Jones face detection in place now. So as you can see, they detect faces fairly well, even though there are some good number of faces are missed. So what is main important here is false detections are less, in the sense that saying a non-face as face is very less, but they may miss the faces out. Okay. So this is sensitive to noise and so on, lighting conditions and so on, but it is very fast in terms of performing real time. It works with like the faces when they are frontal and with no rotations. So there are good number of limitations, and subsequently there are good deep learning methods that has outperformed this face detection approach. We will discuss that subsequently at some point. So it can be applied in general. So any questions on this before we conclude the class?
So can you share the PPT after that?
Yeah, sure. I will share the PPT. Yeah. Okay. Any further questions on or any point that you have not very well understood?
Sir, how the scales were, we were a little confused in the start, right? Like faces at different scales will give different values. So how these scale problem is tackled using this classifier?
Okay,
Since the
scale
size of
problem
the
is not
rectangle
being
is
tackled
the
by
size.
classifier. Scale problem is tackled by feature extraction because they take actually the features at different scales. So that is all these put together are these many features. So what happens is if the face is in this scale in one image, or the face like eyes to nose is in this scale in one image and in this scale at the other image, then it will be captured here, not here. So if it is in this scale, it is captured in with this feature when we convolve with this feature. Otherwise, if it is this scale, it is captured at this feature. Similarly, if we take this region eyes to the nose region, if this is at this scale, it is captured here. If it is bigger, it will not be captured here. It will be captured in other feature or when we convolve with other scale.
So sir, then it has to like move to the entire image, right?
Right. That's what I'm saying, right? So this feature will keep moving on the entire image, also at different scales.
Okay.
All scales. Ranging from this. That's why we have these many features. The main problem now is, since we have these many features, the problem is how do we select out of these features only few features, and how do we make combination of these features as a good classifier. The procedure they follow is, with each feature now being a classifier, what they do is they compute the error across the whole image database. So they have the label here and the image here, and then the classifier response saying face or non-face. This error they will compute on one image. This is one for one image, and across all images they sum this error initially with equal uniform weight. And this is the what this epsilon j is the jth classifier error in classifying all the data samples as face or non-face correctly. Okay, like that they have actually 160,000 classifiers, each giving their corresponding errors. Then they will sort and take only top 20 weak classifiers. Now what we want to do with this top 20 weak classifiers is, you start with equal uniform weights, and then you compute the like the error and so on. This beta value is such that if there is a higher error, you increase the value of beta. That means what happens? You increase the weight. So what happens? Initially, the first classifier is not able to classify it. So now you increase the weight now when for that sample, that image, when you are trying to classify with the second classifier, so that that image gets more focused. Okay. And that will be correctly classified by the second classifier. Now, even second classifier might miss some of them in some of these samples, image face samples classifying correctly. Then those samples weight will be increased in the next iteration. Okay, third sample will classify correctly. At each stage, what they do, instead of like the combination of these weak classifiers is the one which is a finer classifier. With this, if you see, is it correctly classifying or not? If it is not correctly classified, those samples weight keep increasing still further. And the subsequent, when you add a next classifier, it will be able to classify it better. Finally, a combination of this will classify them with very small error. Then you can consider it as converged. Is this clear?
Yes, sir. So it's kind of a recursion until and unless we find good classifiers.
Correct.
And then we sum those classifiers to form a strong classifier.
Correct. And the weights are also in such a way that actually both this beta value and this alpha value are proportional to the error. that it classifies a particular, what is the error? It incurs, a particular classifier incurs on the whole image database. Like that, they perform in a recursion or in a sequential manner rather than recursion, in a sequential manner, and then classify it.
Okay, got it, sir. Thank you.
Fine then. Anyway, I suggest you people also to go through once, and we can discuss if you have any doubts or questions on this. And then in the next class, let's move on to the scale invariant feature transform, which is also an elegant method used for feature extraction and description, which is almost the highest cited paper in computer vision, with 65,000 citations by now. Let's discuss that, and then we will move on to different computer vision tasks. So how understanding computer vision tasks and one example solution for each of the tasks. How classical computer vision methods are for dealt for each of the computer vision tasks, that we will see with a single example algorithm. Okay, and then subsequently we will move on to the deep learning concepts. Thank you then.